will now continue with section 3.1, relations and functions. We will begin with a definition for a function. A function is a relation in which every element of the domain is paired with exactly one element of the range. In other words, a function is a relationship in which no two distinct ordered pairs have the same first coordinate. In other words, to say that something is a function is saying that all of the x values have to be different. Note that it does not say anything particular about the second coordinate or the y values, but if you have a function, all of your x values must be unique. With that in mind, let's look at a few examples. For each relation in example 1 that we did in the last video, identify whether the relation is also a function. So our first example was an example where we were given 5 ordered pairs. So now the question is, does this relation represent a function? So we will look solely at the x values, and we will make sure that all of the x values are different. If they are, we have a function. If they're not, then the relation is not a function. Note that you have two x values that are -4. So this is not a function. You can see that illustrated as well from the graph. We are not allowed, if we're going to have a function, to have something like this, because these 2 points have the same x value. This is the point -4, 0, and this is the point -4, 2. And again, we have that duplication of x values that is shown in the previous example. So this is another way of looking at that same example and concluding that no, it is not a function. Part B of our problem was to have an equation, -3x plus 7y is equal to 13, and they're asking us, does this relation represent a function? Remember that the graph looks like what we have on the screen. Also remember that we talked about that the domain consisted of an infinite number of ordered pairs. But note that we don't have any 2 points that are aligned vertically, like we saw in the previous graph. So since there are no 2 points that are aligned vertically, then we can assume that this does represent a function. For part C, we had the graph shown on the screen, which is a rectangle. The question again is, does the relation represent a function? And the answer in this case is no, it does not represent a function because you do have points that are aligned vertically. If you look at this point and this point, for example, both points on the graph, and yet those points have the same x values. This is the point -1, +1. This is the point -1, 2. The points have a common x value, and therefore this is not a function. The fourth example that we looked at previously was very similar. It was a rectangle, but instead of being the outline of a rectangle, it was the solid shape, indicating that the domain and range consisted of all the points, even on the inside of the graph. This is also not a function for the same reason that the last one was not a function. If we pick 2 points, and I'm going to purposely pick the same 2 points, these 2 points, -1, 1 and -1, 2, have a duplication of x values. That alone makes it not a function. We'll now look at what is called the vertical line test. If a relation can be graphed in the Cartesian plane, the relation is a function if and only if no vertical line passes the graph more than once. If even one vertical line intersects the graph of the relation 2 or more times, the relation fails to be a function. What this is saying is if you have the graph of a function, for example, let's suppose that our graph looks like this. The vertical line test says that we are to draw a vertical line, and if that vertical line passes the graph in only one place, then it is a function. So let's try this. If I draw a vertical line here, it only crosses the graph in one place. If I draw a vertical line here, it only crosses the graph in one place. If I draw a vertical line here, it only crosses the graph in one place. This is a function. As long as my vertical line only crosses the graph in one place, then it is a function. If, on the other hand, we had the graph of, say, a circle, and I wanted to do the vertical line test, and I drew my line here, that line crosses the graph in 2 places. That means that it is not a function. So let's look at our same examples, or at least some of the same examples. This is the same type of example we looked at the beginning, where we have a set of ordered pairs. Does it pass the vertical line test? If I draw a vertical line here, it only hits it in one place. If I draw a vertical line here, it only hits it in one place. Here it crosses the graph in one place. Here it crosses the graph in one place. Here it crosses the graph in one place. This does pass the vertical line test, and it is a function. What about this one? If I were to draw my vertical line, and you can see that it's kind of sketched out for you here. If I were to draw my vertical line here, note that you cross the graph in more than one place. And so what that means is that this is not a function because it fails the vertical line test. What about this one? If I draw my vertical line here, I'm only crossing the graph in one place, so that is okay. What about here? Only crossing in one place, that is okay. What about here? Only crossing in one place. Since each line only crosses the graph in one point, then it is a function.